Good morning, students. My name is Courtney Grimes, and I teach at Denton Magnet School of Technology. I'm the Math 6 as well as the middle school algebra instructor there. Last week, we talked about two-way tables with bivariate data. Today, we're going to extend that understanding through scatter plots, and then we're going to create a line of best fit. Our standard, as always, indicates our goals for the lesson. So for today's lesson, we're going to represent data on a scatter plot, and we're going to describe how the variables are related. So let's get started. So here we have an image of a scatter plot. By definition, a scatter plot is a graph that shows a set of data that has two variables. And remember, when we're looking at the relationship of two variables, we consider that to be a bivariate variable. So the information that's represented on our graph is looking at the variables between time studying and test scores. So I'm going to briefly go through the table, and I want you to see whether or not you can recognize the relationship. So if a student spends 45 minutes studying, they receive the score of 89%. If a student spent 30 minutes studying, they receive the score of 78%. When a student spent 50 minutes studying, they received a score of 90%. 60 minutes of study time received 92 on the test. 40 minutes of time studying received a score of 85%. 48 minutes received a score of 87. 55 minutes, a score of 95%. And finally, 35 minutes studying, that student received an 82%. So what we did was we took all the data that was in our graph and we plotted the points. Now notice that the points did not form like this really beautiful straight line or this beautiful curve. Instead, the points are scattered, hence the scatter plot. Now, do you notice anything between the time spent studying, which is represented on our x-axis, and the test score? If you haven't, by the end of today's lesson, you'll recognize that there is a relationship between the time spent studying and the test score, and we can see it in the table as well as on our graph. Okay, so when we're looking at scatter plots, they can be either linear-like or nonlinear. And I say linear-like because if you can remember from second and third quarter, when we were studying linear relationships, we had this perfect straight lines when we plotted the dots. Well, when we're plotting scatter plots or graphing scatter plots, we don't get that perfect line. So instead, we get dots that are kind of all over the place. But, however, they have like this nature, this trend-like. So if we have a scatter plot, and the trend looks like a line, we'll say that that scatter plot is linear. If it does not look like a line in nature, we'll say that it is nonlinear. Here are some more examples of nonlinear scatter plots. Now, notice that for my black scatter plot, it does not give me a line-like, but it does give me that curve-like relationship. And this particular curve looks to be exponential. So scatter plots are not always linear. They can take on other relationships like exponential as well as quadratic. But for today's lesson, we're going to focus on linear and nonlinear scatter plots. Same is true for my green scatter plot. Notice that it does not look line-like, so it's not linear in nature. However, it is curving upwards. So as x is increasing, y is increasing, but it tends to kind of level off and become constant after, say, x is 6. It tends to level off and become constant. That is another scatter plot that looks exponential in nature as well. If a scatter plot is linear, we have what we call a correlation. In today's lesson, I'm going to refer to the correlation as association. Just remember that those are the same things, okay? So let's take a look at our blue scatter plot. Do you notice a trend in our data on this graph? Remember with linear relationships, as x increases and y increases, we say that it has a positive slope. So we're going to use that exact same reasoning when we're referring to positive and negative relationships or associations on scatter plots. So for my blue graph, notice that as x increases, y is increasing, so my line is taking an increasing approach. So that's a positive association. Now if we look at our red graph, as x is increasing, what's happening to the y values? As x is increasing, the y values are decreasing. Now, we tend to say that that is negative in relationship. Since we're talking about the scatter plots, this is a negative association. If we have a scatter plot that's unique, like our purple scatter plot, it looks like it's forming a horizontal line. So it's still linear-like in nature. However, this association is neither increasing or decreasing, so we say that it has no association or no correlation. Okay, so let's take all of that and let's put it together in one big picture, going back to our information about time spent studying and the test score. There are three types of linear association that are possible for scatter plots. What are they? If you said positive, negative, and no association, you're 100% correct. So now let's look at our graph for a test score versus time spent studying. Which one of these associations is represented in our scatter plot? Well, notice that as time spent studying from 30 to 60 minutes, the test score increased from 80 to 95%. So as x increased, y increased as well. So if we're trying to determine the association that's represented here, we'll say that this graph represents a positive association. So let's continue our practice of identifying positive, negative, and no associations with linear scatter plots and whether or not the scatter plot was linear in the first place. So here we're looking at the relationship between the ice cream cells versus the temperature. So if you look at the x-axis, our x-axis represents the temperature in Fahrenheit. My y-axis represents the ice cream cells in dollar amount. So as the temperature increased from 50 degrees Fahrenheit to 80 degrees Fahrenheit, you can see that our data increased in cells from $200 to $500. So as x increased, y increased as well. And if I look at that like nature, it looks like the scatter plot is increasing like a line does on a linear function. So it's definitely linear, so we'll get rid of A. It is increasing, so it's a positive association. So this is a linear scatter plot with a positive association. So our answer here is B, a linear relationship with a positive association. Let's take a look at another example. What kind of association is shown in this graph? Is it A, nonlinear, B, linear with a positive association, C, linear with negative association, or D, linear without association? My graph is representing the number of clothing layers worn versus the temperature. My x-axis represents our temperature in degrees Fahrenheit, which ranges from 20 degrees Fahrenheit to 80 degrees Fahrenheit. My y-axis represents the number of clothing layers worn. So as I analyze my graph, as the temperature increases from 20 degrees Fahrenheit to 80 degrees Fahrenheit, the items of clothing worn decreases from 4 to 1. So if I look at the like nature, it is definitely decreasing. So it's linear. It looks like a line. So that gets rid of A for us. So it's either positive association, negative association, or no association. Since my line is decreasing, or the relationship between the two variables have a decreasing relationship, this is a negative association. So for this example, our answer is C. The scatter plot is linear with negative association. This last example I would like for you to attempt at home. What kind of association is shown in this graph? Is it nonlinear? Linear with positive association? Linear with negative association? Or linear without association? And I'm pretty sure some of you guys have already answered the question. You notice that it is a line-like and that it's increasing. So as I'm looking at the shoe size versus the height measured in inches, if the shoe size ranged from 5 to 9 and the height ranged from 55 to 75 inches, as the shoe size increased, the height in inches increased as well. So that leaves me with a linear scatter plot with a positive association. What association is shown in this graph? This time we're looking at the relationship between the boy's height versus his weight. You can look at this graph and notice that there's this little curve that's taking place. And it takes place between 50 inches to 65 inches. Since there's a curve, we know that it's not linear. And since it's not linear, it's not going to have a positive association, negative association, or no association. Therefore, our answer here is A. This is a nonlinear relationship on the scatter plot. Okay, so now that we know how to read a scatter plot, we're going to move into creating a line of best fit. Bivariate data plotted on a scatter plot shows us negative or positive association. And remember, association is similar or the same as referring to correlation. A line of best fit, or the trend line, can help us predict outcomes using the data that you already have. It is drawn on a scatter plot that best fits the data points. So let's look at drawing this line of best fit, looking at test scores versus time spent. If you can remember, when we plotted the data, it gave us a linear-like nature, and it was positive. However, we could not draw a straight line to connect all the dots. So instead of trying to draw a straight line to connect all the dots, we're going to create a line of best fit. And just like with clothing, we just want the line to fit the data. So notice that the points form a linear-like pattern. To draw a line of best fit, we're going to use 2 points so that the line is as close as possible to the data points. So this line will definitely not hit every single point that's on the scatter plot. However, we want it to fit the data as close as possible. So here, our line is drawn so that it fits as close as possible to the data points. Here's a little trick. The number of points above and below the line should be about the same. So if you look at my red line, I definitely intersect 2 points, but if I look above the red line and then I look below the red line, the goal is to get about the same number of data points above and beneath it. There are 3 points above our line and 3 points that are below the line. The line was drawn through the point 3582 and 5090. Using the line of best fit shown in the graph, let's predict the score of someone who spends 32 minutes studying. So this line is going to help us draw a conclusion and make further predictions for data that's not represented on the graph. Here we want to know, what can a student possibly score if they spend 32 minutes studying? So let's see if this is going to work for us today. So I'm going to look at 32 minutes on my graph. Is that going to be my y-axis or is that going to be my x-axis? Well, time is represented on the x-axis. Now I need to locate where is 32 on the x-axis, and you have to be very careful here. When you're reading information on a graph, you have to be very precise. So as I'm reading my x-axis, I notice that it goes from 30 to 40, but then there are little tick marks in between 30 and 40. I have to know what those tick marks represent. Here I see that there are 5 tick marks between 30 and 40. So we must have counted by 2's on the x-axis. Since that's the case, we're going to go from 30 to 32, not 31. So when we get to 32, I can take my graph, move up to my line of prediction, also known as the line of best fit, and I want to intersect that line from 32 on the x-axis. Now I want to see what is the numerical value of the y-axis when it intersects at 32 on the x-axis. I just move over to the y-axis and notice that I intersect at 80. So if a student spends 32 minutes studying, they can expect to score an 80% on their test. Let's do one more example. Predict the test score of someone who spends 48 minutes studying. So again, we're looking at time in minutes, and we want to locate 58 on our graph. Time is represented on the x-axis, and remember that we're counting by 2's. So I find 50, then I have 52, 54, 56, 58. Now that I've located 58, I'm just going to travel up my graph to where 58 intersects the line of best fit. And since my goal is to determine the test score, I'm now going to travel over to the y-axis to determine that value. Now notice there's not a numerical number there. So once again, we have to understand what are the values of each tick mark. Well, if I look at the y-axis between 90 and 95, there are 5 tick marks. So it's very evident that we're counting by 1's on the y-axis. So if a student studies for 58 minutes, I travel up to my line of best fit, and then I travel over to the y-axis because that's where our test score is located, and notice that it is right beneath 95. So if a student spends 58 minutes studying, that student can expect to score a 94% on their test. Okay, so just as a quick practice, a scatter plot is shown on the coordinate plane. Here's our scatter plot. Which of these most closely approximates the line of best fit for the data in the scatter plot? So again, here's the scatter plot, and we want to determine which one of these graphs best represents the data with the line of best fit. If you look at A, we intersected 2 or more points, that's good, but do we have about the same number of data points above the line of best fit as well as beneath the line of best fit? So if I'm looking at option A, it looks pretty good, but let's go ahead and analyze the other ones to make sure that we're going to go with option A. If we look at option B, whoa, we intersect 2 points, but do we have the same amount of data above as well as beneath that line of best fit? And it is very evident that there are more points above my line of best fit than beneath it. So that's not a good representation of the scatter plot with the line of best fit. Let's look at option C. So we intersected 2 points, that's pretty good. But do we have the same amount of data points above the line of best fit as well as beneath it? And it's very evident that it is not. So C is not a good option either. And then finally, let's look at option D. So again, we were able to intersect some points, that's good. But do we have about the same amount of data points above the line of best fit as well as beneath it? And the answer is no. So we're going to go with option A. Option A has a line of best fit that best represents our scatter plot. Okay, so here's the fun stuff. We're going to create a prediction equation. In order to create a prediction equation, we will have to remember how to first find the slope of a line and then how to find the y-intercept of the line. If we're talking about linear scatter plots and we want to write the equation for a linear-like relationship, we have to have a slope and we have to have a y-intercept. So let's get started. We're going to use the 2 points that form the line to write an equation. So the 2 points that we used were the points 35 and 82, and I'm going to highlight those for you. We used 35 and 82, and we used 50 and 90. Now remember, to find the slope of a line, which is m, let me erase that. Get our pen. Slope of a line is m. We do the change in y values to the change in x values. So if I look at my y values, which is my numerator, I have 90 minus 82, which is 8. The change in x values will be 50 minus 35, which is 15. So the slope of this line is 8 over 15. Now we need the y-intercept. In order to find the y-intercept, we just need 1 point from the line, and we need our slope. So here we have our slope of 8 over 15, and our point is going to be 50, 90, where 50 is x and 90 is y. Doing a little calculation here, 8/15 times 50 is 80/3. We subtract 80/3 from 90 and we get 190 over 3. So now we have our y-intercept. And students, I apologize, but we're a little out of time. But when we pick up next week, we're going to start with our line of prediction. We're going to take the equation and we're going to make predictions from our scatter plot. And we're also going to go ahead and get started with our sequences as well. So that's it for today. I would like for you guys to stay safe and have an absolute wonderful weekend. Bye, guys.